coming up. So we've got Sterling Watson and Abe Schneider from Natal Energy US. And we'll just get you kitted up.
All right. So hi, everyone. My name is Sterling Watson, and I'm presenting today with my colleague, Abe Schneider. We're going to be talking about our work and our company's work to design turbines to maximize safe passage of fish while respecting conventional design constraints like efficiency and form factor. We're visiting from San Francisco, so it's a real honor to be here in Norway and to be a part of this conversation. So on the slide here, this is a sample of some of the organisms that are passing through hydropower turbines all the time. And something that we would like everyone here to consider is what role do turbines have to play in the greater goal of sustainable hydropower if they're able to allow animals like these to pass through them without injury. So something that's been pretty evident from the variety of talks that we've heard so far this week is that sustainable hydropower is a very complex issue. And there's no one solution that's going to solve all the issues that we see with hydropower's effect on the environment. However, something that every hydropower plant has in common is that it has at least one turbine. And at any hydropower site, there may be a variety of factors that affect how many fish and what species and life stages and sizes are passing through that turbine. But in general, it's very hard to keep absolutely everything out. In the context of thinking about the EU taxonomy, we need to consider all technically and ecologically relevant measures to provide for good ecological potential, and the turbine should be a part of that. So in the illustration here, this is a drawing of a conventional hydropower plant, and at its core is a turbine which has been designed to allow for safe passage of fish, or to maximize safe passage of fish. And so the question really is, how safe can a turbine be for fish, and under what conditions?
Thanks. And I think I would add to that if we want to make a difference and allow for true scaling of fish-safe turbines, these turbines actually must meet really stringent criteria. In fact, it's important that these turbines allow for operation in a conventional manner. That's why on the previous slide, we show a conventional hydropower plant. This means that fish-safe runners actually need to rotate at the same shaft speed as a conventional machine in order to have broad relevance to the fleet. They need to be installed in the same setting, the same position above tailwater, and they need to use the same water intake, the same water passageway, the same draft tube. Our work in this area has led us to a couple of fairly simple combinations of turbine blade features that can allow for rotor to run as fast as possible, to rotate as fast as possible, and yet respect physiological limits of fish. So on the left is a turbine designed according to the principles that we'll get into in our talk. And on the right is a cartoon or an illustration of a conventionally designed propeller. And some of the salient differences that you can see are that the left-hand rotor has extremely thick blades, on the order of 10 times thicker than a conventional turbine blade. But the blades are also noticeably swept forward in the direction of rotation, and this forward sweep allows for a reduction in the normal component of the strike velocity that fish feel out at the maximum radius, where the tangential speed of the runner is highest. Next. So these types of runners can be integrated into any typical water passageway. What we're illustrating on this slide is an axial flow pit turbine. And so water flows from the left through a series of guide vanes. These can be adjustable wicket gates, and then they enter the runner. The runner, importantly, because of the way that this runner has a very prominent forward sweep, it actually also eliminates the possibility of pinch points. In a classic Kaplan shape, sometimes the leading edge of the blade is actually swept backwards, and this creates an additional risk for fish, as fish can be pushed into a converging cavity where they can then be trapped and impinged, and in some cases then cut. Importantly, though, this type of runner is an axial flow. It's a general purpose axial flow design, and it can be integrated with radial inflow type of intakes, or it can be integrated in an axial flow form factor as well.
So this talk is about turbine design. And the first question to ask in designing for fish safety is, what are the factors that cause fish injury and mortality? And one of the primary causes is direct collision with blades. This issue of blade strike is something that has been studied, isolated in the laboratory. So what you're looking at here is the linear strike flume at Alden Laboratory in the United States. This was used to study a couple of parameters that affect strike survival, which are the length of the fish relative to the thickness of the blade that is coming into contact with it, the L to T ratio is what it's called, as well as strike velocity. And in our design work, we wanted to additionally study the effect of this blade slant. So the angle that the leading edge of the blade makes with the oncoming flow or the oncoming fish. The way this works is this is a long linear flume. It has a set of rails, and various representative blade geometries can be attached to those rails and propelled at an anesthetized fish in the viewing window. And then that entire process is caught on high-speed video, and injury and mortality are quantified. So we conducted this study at the Alden Laboratory facility with 1,700 rainbow trout. This work was published in 2020, so you can learn more there. But a couple important things. One of them was that we were asking the question, do these thick slanted blades improve survival outcomes at elevated strike speeds that are representative of the speeds in conventional turbines? And the answer that we saw was yes. But the other really valuable thing was the high-speed video. So being able to understand what happens, particularly in this low L to T situation where the fish is relatively small relative to the blade, how is this actually creating the improved strike survival outcomes? And so just to get into this a little bit, we analyzed all the high-speed videos and quantified the speed of the fish and the speed of the blade. What matters is the relative velocity. That's the velocity of the strike that the fish feels. And when the L to T ratio is low, the fish is essentially pushed by the stagnation region, the pressure wave in front of the blade. And this can act to push the fish out of the way of the blade, or at least to reduce the actual velocity at which it is struck. And you can see from the scatter plot here that at L to T ratios of 1 or below, this relative slowing can be as much as 30%. So that's actually really significant for contributing to the higher survival rates that we saw. So we conducted the isolated blade strike work, built models off of that, but another really important step for understanding what happens to fish when they pass through the turbines is putting all the pieces together and directly studying turbine passage, and not just for rainbow trout like we had worked with in the laboratory, but with a variety of species. So this is an overhead view of the hydraulic testing facility that we have at our office in California. The way this works is it's constantly recirculating, pumped loop. It was actually originally designed to allow for conventional performance testing, but really crucially was adapted to allow us to readily pass fish through the turbine, observe their passage by means of this transparent runner housing and high-speed video, and then extract the fish from the flow with a fine wedge wire screen and immediately observe their condition after being exposed to the turbine. So this has been the foundation of quite a lot of the work that we've done and continue to do. So a few of the tests, a few species of note that we've been able to work with in the last few years. We started with rainbow trout. This is where a lot of that initial strike work was done. They're a good species to work with, a good representative salmonid. And we've done testing with rainbow trout at a variety of size scales. So what you're looking at in the video here is from a camera inside a 1.9 meter diameter turbine. And the size of fish that we tested at this site ranged from 20 to 53 centimeters. We've also conducted quite a lot of work with rainbow trout on the smaller scale facility that I showed you in the previous slide. I think I forgot to mention that turbine is 55 centimeters in diameter, so it's quite small. Another important test that we conducted was with juvenile alewife. These are an important migratory species on the east coast of North America, and they're differ from salmonids in some ways. Notably, they're known to be extremely fragile, especially at this life stage. So that's why we wanted to study their passage. This test was conducted in the field with a transparent housing that we brought to the site and installed with high-speed video cameras. And what I really like about this video is we actually were passing about 250 fish at a time through the turbine. So you can see how the fish move through in different positions, different orientations, but in no case are they actually colliding with the blade in what we would characterize as a severe strike. And that matches up with the very high survival rates of 98 to 100% that we saw. And then finally, American eel. Eels have been a point of discussion a little bit in this conference. Certainly in the United States, they are one of the driving species that are affected by hydropower, and that's because of their ability to enter turbines despite being quite large. So this was our most extensive test that we've conducted. It was pretty extreme parameters in that the turbine was 55 centimeters in diameter, but the eels ranged from 34 to 65 centimeters in length. And it was really important to study eels because they have such a different morphology from the salmonids, and to capture this high-speed video to see, how they actually pass through and how that affects their condition when they come out. So this is just another look into an extension of the eel testing work that we did. This was conducted after our official test, so it's not included in the publication of that work, but we wanted to understand what happens if the eels pass through the turbine again, because this is a really realistic scenario for these fish that need to pass, in many cases, multiple hydropower plants to get to the ocean. And so looking beyond direct injury and mortality, we wanted to understand how the fish's condition is affected by multiple passages. So this video, or this series of videos is immediately before and immediately after the eels pass through the turbine over 2 occasions that were separated by a period of 1 week. And again, we saw 100% survival of these eels that were passed through the turbine twice. And so that's very, very much in line with what we would want to see for eels that have to pass through turbines.
Okay, so I would like to help understand where these results lie in the context of some other tests that have been done with eels. So this slide has a plot of individual single passage tests of eel at multiple other hydropower facilities with different types of turbines. On the x-axis is the blade tip speed of the turbine, and on the y-axis is the eel survival rate. And the orange dot here is the turbine that Sterling just described. Just noting some other very successful tests with eels. The VLH has been tested in France with 100% passage or 98 to 100% passage of eel. Some other innovative turbine types have been tested with relatively high rates of passage, but these turbines have very, very low tip speeds. They're very low rotational speed devices. And what's really important in order to find solutions that make sense to most of the existing fleet is to be able to show safe passage with very high tip speeds. And the Natal turbine that Sterling described is already the highest tip speed turbine to have been shown to have 100% safe passage of eel to date. But that's not where we're stopping. We're in the middle of a design process to increase the speed. The pointer is not working, but basically we're working to increase the safe tested speed to above 30 meters per second. And the reason that this is so important is that in the world of large axial flow turbines, this is around the speed limit for conventional Kaplan turbines. Next slide. Okay, so where can these types of designs apply in the fleet? The green stars on this plot, which is on the x-axis the flow rate through a single turbine, and on the y-axis the head through a single turbine with diagonal lines representing the power of each of these turbines. All of the green dots are basically references for RHT runners of the type that we've been describing. And as you can see, all of these green stars are effectively small or micro hydro sized turbines. But this year, we are working on 3 different projects in different stages of advancement to apply the design techniques for this turbine to much, much larger machines, which span individual turbine flow rates from 70 to nearly 200 cubic meters per second at significantly higher heads of up to 30 meters. And so this results in individual turbines with between 25 and 50 megawatts per turbine. So we think that this work will help provide for usable options to provide safe fish passage across a very wide range of the low head hydropower fleet. And so in conclusion, I think this is the prompt that we wanted to provide, which is as new data emerges that shows the ability of conventional turbines to provide for truly safe fish passage, can we consider the turbines as part of a tool set to achieve good ecological potential?
I think we're out of time.
So thank you very much.
Well, thank you very much.